So hello and welcome to week 3 of the MA106 Category Theory course. So my name is Shubhajit Das and I'm a PhD student in the Department of Mathematics at IISc. And each week we solve problems based on the lecture material covered in the course. So I'll just give a brief summary of what exactly has been covered in this particular week in the course. So in this week, what you learned essentially is the following: that spatial properties of morphisms in a category. So you saw what is a monomorphism, what is an epimorphism, you saw what is an you already knew what is an isomorphism. Am I audible?
Yes, you are audible.
Okay. Yeah, so I was just saying that in this week you saw some special properties of morphisms in a category, right? You saw what is a monomorphism. You saw when is a morphism called an epimorphism, and you already knew what an isomorphism is, right?
Yes.
Yeah. And there are some other special kinds of morphisms, right? You know what is a bimorphism. So a bimorphism, just to reiterate, is exactly an arrow in a category which is both monic as well as epic, right? So an arrow which has both properties is called a bimorphism. An arrow which is both left cancelable as well as right cancelable is called a bimorphism in a category. You know what is an endomorphism. These are some special kinds of morphisms in a category. So it's exactly a morphism whose domain object is equal to its codomain object. And then there is this notion of automorphism, which I'm sure you have studied previously in specific contexts. But in a general category, it's just an endomorphism, which is also an isomorphism. But that was not all that was covered during this week, right? You also studied the famous Yoneda Lemma, and perhaps one of the most important results in category theory and throughout mathematics, right? Which intuitively basically says that, or answers the question that what do representables in a category essentially, representables on a category essentially see, right? So Yoneda Lemma answers the question, what do representables see? In the sense that what are exactly the maps coming out of the representables, or what are the natural transformations whose source is a representable functor, right? And the answer to this question is they see elements, right? That's what you learned. That is what the Yoneda Lemma says. It says that given a category A, an object A in it, and a functor f from A to set, a natural transformation from this representable functor to f is the same as some element Fa, of the set Fa. This is what, so this is what the Yoneda lemma says. And it turns out that this philosophy is enough to understand mathematical objects, right? I mean, that is the idea of category theory, right? It's like it's only the relationships that matter in category theory. You are not interested in what is internal to a mathematical object. You don't care about what is inside a mathematical object. The idea is to understand how an object is related to other objects in terms of what are the maps coming out of that object, or what are the maps going into that object. And the Yoneda lemma says that this perspective is enough to know the mathematical object up to isomorphism. So Yoneda lemma is basically a concrete proof of the fact that the philosophy of category theory is enough to do mathematics, in the sense that it's like an alternate way of doing mathematics without having any internal look on objects. So you studied the Yoneda lemma, you studied the Yoneda embedding, which is exactly a functor from a category into its okay, let me just write it, into the category A op comma set, this functor category, right? And one of the consequences of the Yoneda lemma is that this Yoneda embedding functor is actually fully faithful, right? Which is exactly the perspective that one takes to characterize mathematical objects, right? So basically, in other words, if y of an object A in script A is isomorphic to y of an object A prime in script A, by which I mean that if this functor is isomorphic to this functor, then this implies that, in particular, this implies that A is isomorphic to A prime. And not only so, the isomorphism at the level of functors is induced by an isomorphism at the level of objects, right? But forgetting that for the time being, the idea is that fully faithful functors reflect isomorphisms, in the sense that if you start with a morphism in script A, take its image in the functor category, which is a morphism in the functor category and therefore a natural transformation in the functor category. If this image, that is, if this natural transformation happens to be an isomorphism, then the original morphism that you started with in script A is also an isomorphism. So this is what the Yoneda lemma says, that if you look at the functor which is represented by A, and if you look at the functor which is represented by A prime, and if those two are isomorphic, which in particular means that maps from an object B into A are essentially the same as maps from an object B into the object A prime. If this happens for every object B in a certain nice way, then A is the same as A prime. So to understand an object A, all you need to understand is what are the maps going into A, and that is all. That is enough to know A up to isomorphism. This is the external point of view that category theory, that is a philosophy of category theory. Okay, so yeah, so we'll be solving problems based on the material that you have covered this week, and hopefully we will learn something new. So yeah, let's start. At any point, please feel free to stop me, and if you have any questions. So we start with this very simple first problem, which says that suppose that you have a string of two morphisms which are composable in a category, such that the composite G composed F happens to be a bimorphism. That is, G composed F is exactly an arrow which is both a monomorphism as well as an epimorphism. what you are asked to show here is that the morphism F should be a monomorphism and the morphism G should be an epimorphism. We'll come to the later question later, but for now we just need to focus on showing that F is a monomorphism and G is an epimorphism. So what you know is G composed F, this arrow from A to C is a bimorphism, that is both monic, is both mono and epi. So we can just write, we know that a monomorphism in a category is written like this, right? It's an arrow with a barbed tail, and an epimorphism in a category is written like this, right? So we can combine these two and write it like this. But yeah, okay, I mean that's just notation. So G composed F is both mono and epi. What you need to show is F is a mono, first of all. So how do you plan to show that? Can anyone quickly give me the argument? And please interact. I mean, that is what makes sessions I mean that will benefit everyone. So how do you show that F is a monomorphism? Okay, so tell me, what is a monomorphism again? Anyone? A monomorphism in a category is exactly a left cancelable morphism, right? So to show that F is a monomorphism, what you need to show is, so this is your F from A to B. You want to show F is a monomorphism, you need to show F is left cancelable. In other words, whenever this happens, F compose P is, no, okay, I'll come to that. If whenever F compose P is F compose Q, this will imply that P is equal to Q, right? So F should be left cancelable. F should be cancelable on the left. You can cancel F on the left, right? This should, so whenever this happens for all PQ, such that F compose P, F compose Q exists and F compose P is equal to F compose Q, then P must be equal to Q. If this happens, then the morphism F is called a monomorphism, right? Left cancelable morphism. Yeah. So to show this, what I need to start with two maps P and Q, right? Yeah. Okay, it's fine. So two maps P and Q, and take an arbitrary object X, right? I mean, the condition that F compose P should be F compose Q in particular says that the domain of F compose P, which is the domain of P, should be equal to the domain of F compose Q, which is the domain of Q, right? So both P and Q should have the same domain, which is X. And F is composable with P and F is composable with Q guarantees that the targets of P and Q are both the domain of F, which is A in this case. So it has to look like this. That is what I am saying. The starting data should look like this. So what I need to show is for all objects X and for all arrows P and Q, F compose P is equal to F compose Q should imply that P is equal to Q. Now how do we exactly show this? And we know that G composed F is both mono and epi. So in particular, G composed F is a mono. So take arbitrary P and Q such that F compose P is F compose Q. Then what can I say? Okay, let me write it down. Write it below. Yeah, F compose P is equal to F compose Q. We need to show that P is equal to Q. So P and Q are arbitrary morphisms. What can I do now? I can just compose with G, right, on both sides. So this implies, since composition is a map, you know, so it's well defined, which means that this will agree. So G composed F composed. Okay, so since you know that composition is associative, there is no need to bracket compositions, right? Composites. It's understood. So G composed F composed P is G composed F composed Q. which implies since G composed F is a monomorphism, so it has to be left cancelable. So this implies P is equal to Q. So done. So what we have shown is that for every object X and for every parallel pair of arrows P and Q such that F compose P is equal to F compose Q, we always have P is equal to Q. That is exactly what it means to say that F is a left cancelable morphism. That is, in other words, F is a monomorphism. So since P and Q are arbitrary, so F is a monomorphism. How do you show that G is an epimorphism? We also need to show that, right? G is an epimorphism. How do you show that? How do you show that G is an epimorphism? So epimorphisms are exactly right cancelable morphisms in a category, right? Which means that, so G is from B to C. G is right cancelable means that for every object Y, let's say, and for every pair of arrows C to Y, let's say P and Q, whenever P compose G is equal to Q compose G, this should imply that P is equal to Q. That is what it means, right? For G to be right cancelable. So to show that G is right cancelable, what do we need to show? So we again take arbitrary morphisms, C2 Y P and C2 Y Q, such that we should also say take arbitrary. So take arbitrary P and Q such that such that P composed with G is Q composed with G. Right. We need to show that P is equal to Q. How do you show this? So you already know that G composed F is an AP. We want to show that G is an AP. So what we need to show is that G is right cancelable. So what we need to show is for any arbitrary object C and for arbitrary arrows P and Q, whenever P compose G is Q compose G, we have P is equal to Q. So what do we need to do? Since G composed F is an epimorphism, we can combine or compose with F to obtain P composed G composed F is equal to Q composed G composed F. Exactly. And this again, since G composed F is an AP, this implies P is equal to Q, as G composed F is an AP morphism. And this holds as, let's write it here, as G composed F is a monomorphism. Yeah. Oops. Yeah. So this implies P is equal to Q. 1 second. I think my app has hanged. Yeah. So yeah. So G is an epimorphism. So what have we shown really? We have shown, so this is the problem. So we have shown that if in a category G composed F is both a monomorphism as well as an epimorphism, then F must be a monomorphism and G must be an epimorphism. This is what we have shown, and this is in perfect coherence with your intuition from set theory, right? You have seen that if a composition of two functions of sets is both injective and surjective, then the first function that you start with should be injective and the second function should be surjective, right? The same thing happens here, except that injectivity is replaced by its category theoretic analog, which is called a monomorphism. Surjectivity is replaced by its category theoretic analog, which is called an epimorphism, and which is exactly why, regarding the comment by one second, yeah, Romita, which is exactly why you should understand this very well, that in a category injective maps don't make sense, right? Because to define injective maps you need elements of your domain object, right? But in an abstract category, an object is all that you have, right? It has no internal data, or it has no internal structure. It's just an abstract object, that's all. It's just like a symbol or a dot, that's all, or a blob, whatever you would like to think of it. There is nothing internal to it. It's just a symbol. You treat it just as a symbol. It's a primitive notion. So you can't really define what injective map is in a category. You can't define what an injective homomorphism is. So the right notion is a monomorphism, which sort of is a replacement for injectivity, and is a way of sort of arrow-theoretically capturing what injectivity should be. So a monomorphism is a left cancelable morphism, and the idea is that in the category of sets in particular, in which an object is a set, so in particular has elements in it, an injective map is exactly a monomorphism, and a surjective map is exactly an epimorphism, right? But in an abstract category, an object does not have any internal structure, right? It's just a symbol. It's a primitive notion, that's all. So whenever I say A is an object, that's all that you know about A. You don't know if A has any internal data or A has some property. You don't know anything about it. You just know that A is a letter. You treat A as a letter, as some object. You don't know what it is, right? It might be a set, it might not be a set, right? We have seen examples of categories in which objects are not sets, right? So the idea is to make an abstraction of what you do with ordinary mathematics, right? That is why an object for you is anything, any abstract entity, that's all. It's a primitive notion, as I keep saying. You can treat it just like a dot, that's all, right? An object in category theory has no internal structure. There is no internal structure for an object in category theory. I'll repeat it once again. An object in category theory has no internal structure. An object is just a symbol, just a dot, that's all. That's all that it is. So to define what the right notion of injectivity should be, what you consider is the notion of monomorphism, which is a left cancelable morphism. Exactly, right? This is the way of category theoretically capturing this notion. So you can't make sense of injectivity in an abstract category because you don't have elements in an abstract category. Objects don't have elements in an abstract category. It doesn't make sense to talk about elements. There is no existence of elements. An object is a primitive notion, right? So there is no notion of elements. Objects have no internal structure. So yeah, so you can't talk about injective maps. So that is why the right notion is, the right idea is to talk about a left cancelable morphism. So a monomorphism is a left cancelable morphism and epimorphism is a right cancelable morphism. That's all. Okay. So we have seen that we have proved this, that F is a monomorphism and G is an epimorphism whenever G composed F is both a monomorphism as well as an epimorphism. But here comes the next question, which sort of says that can you use the duality principle to give a shorter proof of this? So can you use the idea of duality to give a shorter proof? So you know what the duality principle says, right? It says that if a certain category C has a particular property, a property which can be expressed category theoretically, I mean in terms of objects and arrows, that's all. Syntactically speaking, just in terms of objects and arrows. I mean in terms of these two symbols. That is what a statement is. So if in a category C, a particular statement holds, then in the opposite category C of, the dual statement will hold. And the dual statement is obtained from the original statement by keeping the object same, just reversing the direction of the arrows and replacing every composite G composed F by F composed G, or if you prefer F op composed with G op. So question is, can you use the duality principle to give a shorter proof? So my point is, I am sure you have already seen this in this particular week. The point is that if F is a monomorphism in a category C, then F op is an epimorphism. In the category C op, in the dual category C op. I'm sure you have seen this. That is, monomorphisms and epimorphisms are dual notions of each other. Can someone confirm if this has been covered in the lectures this week? Anyone? Okay, we'll just quickly mention the idea. So assume that A to B you have a monomorphism F in C. So this is a monomorphism in C, and I'll write the corresponding in C op. So A to B you have an arrow in C F. I write the corresponding arrow in C op by B to A, F op. What I claim is that F op should be an epimorphism, right? So what does it mean to say that F is a monomorphism? It exactly means that F is a left cancelable arrow in C, right? To show that F op is an epimorphism, I need to show that F op should be right cancelable. So what I need to show is that if you take F op B to A, and if you take two arrows P and Q to some object X, let's say, such that P composed F op is equal to Q composed F op, you need to show that P is equal to Q, right? That is, F op is right. This is what it means, that F op is right cancelable, or F op is an epimorphism in C op. So the question is, how do you show P composed F op is Q composed F op? And by the way, since we follow this convention, I'll write arrows in C op by arrows in C power op. So if P op is an arrow in C op, what I mean essentially is P is an arrow in C in the opposite direction. Okay, Q op is an arrow in C op means that Q is an arrow in C in the opposite direction. So we'll write arrows of C by usual letters, and we'll write arrows of C op by the same letters, just supplied with an op at the top, with a superscript op. That's all. So what you need to show is that if P op composed with F op is equal to Q op composed with F op, then P must be equal to Q, right? That is what you need to show. So what happens really in the original category? So F op is from B to A in C op. That means F is from A to B in C. P op is from A to X in C op, means that P is from X to A in C. Similarly, Q op is from A to X in C op, means that Q is from X to A in C, right? And what does this statement tell you? It says that P op composed with F op is Q op composed with F op in the opposite category C op. How are compositions really defined in the opposite category C op? We have seen this in the past 2 weeks, that this is exactly F composed with P op, which is F composed with Q op, right? This is what it essentially means, right? So F composed with P is an arrow in C. Take the op, you get an arrow in C op. This is equal to F composed with Q op. So these two arrows in C op are equal, right? By our definition of C op, this exactly means that the original arrows F composed with P and F composed with Q in C are also equal, right? So given this, we have this, right? Given this equality, we have this equality, right? which means that F composed with P is F composed with Q in C. Now what does that mean? If F composed with P is F composed with Q in C, what does that mean? F is a monomorphism, we already assumed that. So if is left cancelable, that implies P is equal to Q. If P is equal to Q in C, that means that P op must be equal to Q op. The corresponding arrows in C op must be equal as well. Right. So it's pretty simple. So what I'm trying to say is we started with F, which is a monomorphism in C, considered F op, and we saw that F op is right cancelable because F is left cancelable in C. Right? So F op is an epimorphism. In C op. That means whenever F is a monomorphism in C, F op is an epimorphism in C op. And since duality is an involution, by which I mean that if C is a category, if you take C op and then again take op, so C op is just C. So what you get is the result that if F is an epimorphism in C, then F op must be a monomorphism in C op. So what this essentially means is that epimorphisms and monomorphisms are dual notions of each other, right? So how can we use the duality principle to shorten the proof? So suppose that we have already arrived at this. Suppose we have already proven this, that whenever G composed F is a morphism which is both mono as well as epi, then F is a monomorphism. Suppose we have proved this. How can we show that G must be an epimorphism then? So we use the duality principle for this. So this is like an alternate proof. So this is an alternate solution using the duality principle. So first you prove that F is a monomorphism. If G composed F is a bimorphism. Actually this is in fact true in more generality, holds. So this result holds if G composed F is a monomorphism. You don't need to assume that it also has epimorphism property. So G composed F is a monomorphism will imply that F is a monomorphism, because what we essentially used in this proof was that G composed F is a monomorphism. That's all that we used. So first you show that F is a monomorphism whenever G composed F is a bimorphism. Now you want to show that G is a monomorphism, G is an epimorphism, right? So what you do is pass to the dual category. C op. So what happened, what was the data in C? You had A, B, C and two arrows. One is F from A to B and another is G from B to C. If you pass to the opposite category, so yeah, I'd like to call it opposite category instead of this term, but it's the same. So pass to the opposite category C op. So once you pass to the opposite category C op, what happens to the data? So A, B, C, but the arrows are now reversed. So this is F op, this is G op, right? So the result that G composed F is a monomorphism implies F is a monomorphism, holds in any category, right? This result holds in any category. So yeah, sorry. So the result that G composed F is a bimorphism implies F is a monomorphism actually holds in any category, right? Whenever G composed F is a bimorphism, F must be a monomorphism. right? This was proved in the category C, but C is just an arbitrary category, so this result will hold in every category, right? So in particular it will also hold in the category C op, right? So whenever the composition of two morphisms is a bimorphism in a category, the first morphism is a monomorphism. Yes, exactly. So so what you do now is, so what you observe now is, what happens to, what is the property of this composition G op composed with, I'm sorry, F op composed with G op. G op. What is this exactly? This is just G composed F op. Now we know that monomorphisms and epimorphisms are exactly dual notions of each other, right? So if G composed F is a monomorphism in C, then G composed F op will be an epimorphism in C op. And if G composed F is a epimorphism in C, then G composed F op will be a monomorphism in C op. Now since G composed F was assumed to be both in C, it had both algebraic properties. That means that G composed F op should also have both algebraic properties. So this is both mono and AP, as G composed F is both mono and AP in C. Okay, I'll come to that. This is both mono and AP in C, C op, as G composed F is both mono and AP in C. Right, so this composite morphism is both mono as well as AP in C op, right? What have we proved? What was the result that we proved? That in any arbitrary category, if the composition of two morphisms is a monomorphism, is a bimorphism, then the first morphism must be a monomorphism, right? This is what we proved. So this implies, since F op composed with G op in the dual category C op, in the opposite category C op is a bimorphism. So by result 1, what we have is the first morphism, which is G op in this case, is a monomorphism in C op, right? In the opposite category C op. We saw that monomorphisms and epimorphisms are dual notions of each other, which implies G is an epimorphism in C. And that's all. So the idea is we didn't need to prove the result for epimorphisms. It was automatic from the result from monomorphisms, right? And that is the power of the duality principle. That is the power of taking the opposite category. Yeah, so we are calling these notions algebraic because they are defined entirely using algebra, right? You see, in a category you have arbitrary arrows, right? So think of the category as some kind of algebraic structure. It's some class of objects together with some class of arrows, and then there is some algebraic structure imposed on the arrows, right? You can compose two arrows, and to every pair of arrows is assigned a third arrow in the category, right? So it's an algebraic structure, and arrows with special properties are given special names here, right? So an isomorphism is exactly an arrow which is invertible, which for which an inverse exists. This is an algebraic notion, right? Notion of an inverse. Then a monomorphism is a left cancelable morphism, a morphism which can be cancelled from the left. Again an algebraic notion, because this has entirely been defined in terms of equations, right? A monomorphism is defined like this, right? For all P, Q, such that F is composable with P and F is composable with Q. F composed with P is F composed with Q implies that P is equal to Q, right? This is, yeah, so this is entirely an algebraic notion. So these are algebraic properties. Okay. So yeah, that solves the first problem. Let's move on. We'll come to this later. This is not too difficult. We'll come to this later. But for now, let's focus on other problems. And I mean, if we don't have time, I'll leave this as a practice problem. I hope that you know what a balanced category is, right? Of course, it has been covered in the lecture, but to reiterate, a balanced category is exactly a category in which all bimorphisms are isomorphisms. So every isomorphism is always both a monomorphism as well as an epimorphism, but the converse might not be true in many categories. For example, in the category of commutative rings. So what is a balanced category? It is one in which the converse is also true. That is, every morphism which is both a monomorphism as well as an epimorphism is actually an isomorphism. So we'll come to that later. But for now, let's focus on the rest of the problems. So state whether the following statements are true or false with brief justification. So problem, I mean the statement A says that the category AB, whose objects are abelian groups and whose arrows are group homomorphisms, is a balanced category. What do you think? Is this true or false? What do you think? Is AB balanced or not? So AB is an example of a concrete category, right? 1 1 and 1 2 with operation preserving is an isomorphism. Okay, so for that you need to prove something, right? What do you need to prove? So he claims. Let me just 1 second. Let me just see who actually gave this answer. Yeah, Umang claims that 1-to-1 and on-to morphisms are isomorphisms with structure preserving property are isomorphisms. But there is something that needs to be proven here to get to that, or to conclude that it's balanced. What do you need to show? So AB is a concrete category, as I was saying. What is a concrete category, by the way? A concrete category is, yes, exactly. So a concrete category is exactly a category in which the objects actually have set structure. So in an abstract category, an object does not have any internal structure, right? In an abstract category, an object has no internal structure. Or in an abstract category, what should I say? Yeah, and in an abstract category or in an arbitrary category, an object has no internal structure. But a concrete category is one in which the objects have some kind of set structure. I mean, the objects are sets with some structure. So in particular, in a concrete category, an object can be thought of as a set that is can be thought of as having elements in it, having some internal data in it, right? So category AB is a concrete category. The claim is it should be balanced. So we need to show that every morphism which is both mono and AP is an isomorphism, right? So what do we need to show? First of all, what is an isomorphism in AB? It's exactly a bijective homomorphism. That's easy to prove. You can show that invertible group morphisms in AB are exactly isomorphisms. So to show that a morphism which is both mono and AP is an isomorphism, you need to show that a morphism which is both mono and AP is bijective. So you need to show that a morphism which is both mono and AP is injective as well as surjective. So the right idea should be, I mean, you can just have a guess at this. This is like an educated guess, and you can try to show instead that monomorphisms in AB, monomorphisms is a category theoretic notion, mind you again, arrow theoretic notion. Monomorphisms in AB are exactly injective homomorphisms. Injection is a set theoretic property which category theory really doesn't capture or really doesn't talk about, cannot talk about. But for AB, for the concrete category AB, what we plan to show is that monomorphisms are injections, epimorphisms are surjections. So let's quickly show this. And the idea is somewhat like how you do it for sets. Yeah. So consider the category AB. Take a monomorphism let's say from a group G to a group H. We need to show that this map F is injective. How do you show this? So need to show, or rather want to show, F is injective. So take x, y in the source G such that fx is equal to fy. We need to conclude that x is equal to y. How do you show this? So the idea would essentially be to find some object in the category AB which can detect elements of G, which can detect the elements of some group G. This is a concrete category. An object in this particular case has elements in it. You need some object which can detect elements. So in other words, an element of a group can also be thought of as a map from some particular group to that group. What particular group am I talking about? So think about all kinds of abelian groups that you know. Think of some special abelian group which has a special status in this situation. I'm sure you have seen it in group theory. Think about abelian groups. Think about one particular group which has this special status that maps from that group to any group are the same as the elements of the target group. So the group is, and this is also one of the assignment problems. No. The trivial group cannot do so because there is exactly one arrow from the trivial group to any group. So it cannot detect elements. It only detects the identity element. So the trivial group is not it. Yes. Z is the group. So the idea is group maps from Z to G are the same as the elements of G. And in fact, this is one of your assignment problems. So I'll not say much. But the idea is maps from Z to G are the same as elements of G. Right? So in other words, if suppose we take an element little g in capital G, you need to find a group homomorphism from Z to G that can detect this element G in a particular way. The group homomorphism should be okay. Let's leave it as an exercise. Yeah. So the point is that maps from Z to G can detect elements of G. So X and Y are elements in G. So take Z to G, two maps. Let's call this map A. Let's call this map B. You have also this map AF, right? What does the map A do? A sends any n to so A is a group homomorphism, sends any n in Z to n times X, and B sends X, not G, and B sends n to n times Y for all n in Z. This is what the maps A and B do, right? So the fact that fx is equal to fy in particular says something in terms of arrows. In terms of the three arrows which are given here, can you say what exactly fx equal to fy says? Can you capture that arrow theoretically? This exactly says that, so fx equal to fy, since A detects the element x, B detects the element y in G, so, and f applied on x is equal to f applied on y. this implies that F composed with A is F composed with B, and you can indeed check this. So two maps are equal, two set maps are equal if they agree on every element of the source, right? What is the source? It's Z. So F composed A at N is equal to F of Nx. Since F is a group homomorphism, this is N times F of X, and F of X is F of Y. So that thing is N times F of Y, which is F of N times Y, which is F composed with B of N, right? So this equality holds for all N in Z, which implies that the maps F compose A and F compose B are equal. Now F is a monomorphism, which implies A equal to B, as F is a monomorphism. Now what does it mean to say that F is equal to B? A is equal to B. A is equal to B in particular means that A applied at 1 is B applied at 1, right? So this implies, so A is equal to B, and hence A of 1 is B of 1, which implies X is equal to Y. That's all. That is what we wanted to show, right? So F was a monomorphism, F is automatically injective. In fact, the converse is also true, and this is true in more generality actually. But in the case AB, the converse is also true, that if F is an injective group homomorphism, it has to be a monomorphism, because you can always apply the forgetful functor to F to get down to sets, right? To get to the category of sets, right? F is injective implies F is injective as a map of sets, and you know that if F is injective as a map of sets, it's left cancelable, right? So the forgetful functor is always faithful, and hence F must be a monomorphism in the category AB. Right. So we have proved that monomorphisms are injective maps, and in fact the converse is also true, right? In this category AB this happens. And what about epimorphisms? Yeah, so let's conclude. So F is an injective map. If so now assume F is an epimorphism. Now let F let G be an epimorphism in AB. Note that we can't use the duality principle here specifically because of this, and this is important to understand that monomorphisms, epimorphisms are category theoretic properties. They are dual notions of each other, but injections and surjections are not dual properties. They are not category theoretic properties. It doesn't make sense to call one dual to the other, right? Injections and surjections in specific categories are not dual properties, right? Those are just set theoretic properties. They are not category theoretic properties. So we can't use duality principle here. Doesn't make sense to use duality. We have to check this directly. So assume that G is an epimorphism in AB. So yeah, I should write it like this. I have a tendency of dropping out of the margin, but yeah. And let G from let's say X A to B, let's say. Let G from A to B be an epimorphism in AB. We need to show that G is surjective. How do you show this? Idea is to use the exact same idea as you do for sets to show that epimorphisms in the category of sets are exactly surjections. You have to use the same kind of idea here as well. So what is the idea? What should the idea be? So G is a group homomorphism. It has been given to be an epimorphism in AB. How do you show that G is surjective? To show that G is surjective, what you need to show is the image of A under G is exactly all of B, right? Now for any group homomorphism, the image of a group homomorphism is always a subgroup, right? That we know. We need to show that this subgroup is all of the group. Now keep in mind that we are in the category of abelian groups, so A and B are abelian groups, right? So what happens if A and B are abelian groups? So since B is abelian, what can we say? G of A is a what kind of subgroup of B? Any subgroup of an abelian group is always yeah, abelian, it's okay, but I mean when I'm saying that something is a yeah, dash subgroup of G, I'm talking about some property which is only relevant for subgroups. So here the idea is it's a normal subgroup. Which means we can take quotients, right? We can take the quotient group B over GA. So we have A, we have B, we have this G, A to B, and we take this quotient group B over GA. There is a canonical map, a natural map, pi, which is the projection map, sending every element little b to its coset in the quotient group, right? We have this map pi already. To use the fact that G is an epimorphism, we need to come up with another map from B to B over GA such that these two compositions with G are exactly equal, and then we can use the fact that G is right cancelable to conclude that those two maps are same, which will in a particular way conclude that GA is exactly equal to B. But the question is, what other map can we take such that whenever G is composed with pi and G is composed with that other map, the two composite maps are equal. So you need to come up with another map H, let's say, such that pi composed with G is equal to H composed with G. What is pi composed with G really? What is pi composed with G? No. Oh, you mean the identity element of the group? Yeah, exactly. The trivial map. Yeah. So the idea is that pi composed with G is itself the trivial map. And why is that? Because pi of G of some A is the coset of GA in the subgroup in the image GA, right? Now GA is already an element of G capital A, which means that this is just the identity coset GA, which means that everything of A, I mean every element of A goes to 0 under this composition pi composed with G, which means that pi composed with G is the trivial map. So you need to come up with another map H such that H composed G is trivial. Yeah, I got it. So better it's just, I mean we can just take H to be the trivial map itself. So take H to be the trivial map, the trivial homomorphism, right? So A to B, B to G over B to B over B mod GA, we take pi and the trivial map. Now pi composed with G, as we saw, is the trivial map, which is equal to the trivial map composed with G, right? And G is an epimorphism, implies pi is equal to the trivial map. So the projection map pi is equal to the trivial map, as G is an epimorphism. Now what does the trivial map do? It sends every element of B to the identity element of the quotient B mod GA. So pi is equal to the trivial map implies that pi sends every element of B to the identity coset, which implies that for all little b in capital B, pi of B is exactly equal to G of A. I mean the identity coset G of A, right? What does that mean? That means that that exactly means that B is in G of A, right? Because pi of B is supposed to be equal to, I mean by definition pi of B is just the coset of B, right? So the coset of B in GA, I mean with respect to GA, is equal to EGA, which implies that B is in GA. So B is an arbitrary element in B and it's in GA, which implies that GA is all of B, which is exactly what we wanted. So G is surjective. So if a morphism is a monomorphism in AB, it's exactly an injective map, or we have proved that it's an injective map. If a morphism is an epimorphism in AB, we have proved that it's a surjective map. So if a morphism is both a monomorphism as well as an epimorphism in AB, that means it's both injective and surjective, which means that it's bijective, which means that it's a bijective homomorphism, which means that it's an isomorphism. So if a morphism is a bimorphism, that is both mono as well as AP in AB, then it is both injective and surjective, which implies that it is an isomorphism. That's all. So the first statement is true. Statement A is in fact true. It's correct. Okay. Now the next question. So we have seen that in the category of sets, monomorphisms are exactly injective maps, epimorphisms are exactly surjective maps. We know this. But now this question is asking about, so what you are doing is you are taking a subcategory of set. So what is a subcategory, by the way? It's just a category. I mean, given a category D, a subcategory of D is a category C whose object, whose class of objects is a subclass of the class of objects of D, whose class of arrows is a subclass of the class of arrows of D. And since it's a category, it's supposed to, I mean, and it inherits all the structure from D, in the sense that if you take an arbitrary arrow in C, its domain object and its codomain object should be in C. C should be closed under compositions. C should be closed under identities. That's all. Right. So assume that C is a subcategory of set. Then monomorphisms in C are injective set maps and epimorphisms in C are surjective set maps. Question is this true? We know that if the subcategory is all of set, if the subcategory is exactly equal to set, that is if C is equal to set, then this result is true. But is it true for any arbitrary subcategory? You take a subcategory of set, is it true? Is this true? What do you think? So keep in mind that how are monomorphisms exactly defined? Monomorphisms are exactly defined as left cancelable morphisms in a category. And how do you define left cancelable morphisms in a category? You take an arbitrary object X, you take arbitrary maps P and Q, such that that morphism, such that if F composed with P is F composed with Q, then P must be equal to Q. So the definition of a monomorphism depends on the ambient category in which the morphism lies. This is not true for split monomorphisms, right? You have also studied what split monomorphisms are, which I didn't mention in the beginning. So yeah, you also studied split monos this week. So what are split monomorphisms? They are exactly left invertible morphisms. Morphisms are, that is arrows which have left inverses, are called split monomorphisms. So you also studied split monomorphisms. And you also studied split epimorphisms, which are the dual notions. So what are split epimorphisms? Split epimorphisms are exactly those arrows in a category which are right invertible, that is, which have right inverses. So the definition of a split monomorphism, which is this, that it is exactly an arrow which is left invertible, does not depend on the ambient category, in the sense that, I mean, it depends on the ambient category, but the idea is that it should have a left inverse, right? Existence of a left inverse guarantees that it's a split monomorphism. So so if you take a subcategory, as long as that subcategory has that inverse, has that left inverse, then it's still a split mono in that subcategory. But to check something is a monomorphism in a subcategory is a very different issue, right? So yeah, tell me, what do you think? Suppose C is a subcategory of sets, then the monomorphisms in C are exactly injective set maps and epimorphisms in C are exactly surjective set maps. Is this true or false? So if a morphism in a bigger category is a monomorphism, it will still be a monomorphism in the smaller category. Very easy to check, follows easily from the definition. But the converse might not be true. If you have a monomorphism in a smaller category, that might not be a monomorphism in the bigger category, because an arrow in a smaller category which is left cancelable need not be left cancelable in the larger category, because the larger category can have arbitrarily more morphisms, right? More arrows. And it can happen in the larger category that F composed with P is equal to F composed with Q might not imply that P is equal to Q, right? So the class of monomorphisms in a larger category is a subset of the class of monomorphisms in a smaller category, and in most cases it's a proper subset. So my claim is that if you take a monomorphism in the subcategory C of set, it might not be a monomorphism in set. That is, it might not be an injective map. And similarly, if you take epimorphisms in the subcategory C of set, it might not be a surjective set map. So can you give an example of such a subcategory and such a monomorphism which is not an injective set map? It's pretty easy. What do you think? So claim is that this statement is false. Oops. What do you mean by only one as objects, or do you mean exactly one object? I mean, yeah, exactly one set. C should have exactly one set. That is what you are suggesting. Okay, can you give me an example now of a morphism which is a monomorphism? So the idea is, I mean, taking one object as set, so you need to, I mean, are you taking the full subcategory? Then that would that might create some conflicts in creating an example. I mean, it will also work, but even a better idea is to consider this subcategory. So let's say, yeah, so let me conclude this. Option A is incorrect. Option B is, sorry, option A is correct. That is what we proved. Statement A. Statement B is incorrect. So take this subcategory. C is this subcategory. By the way, your example can also work, but needs some, I mean, you need to be careful. But let's take this. Let's take a 4 element set, 1, 2, 3, 4. This is one object in your subcategory. Take let's say a 3 element set, A, B, C. this is another object. So this is your object A, this is your object B in the subcategory, and you take two arrows, that is two set maps. I'm sorry, you take one arrow, that is one set map, which is this F. What does F do? F sends, I mean, F is defined in this way, that F sends 1 to A, let's say, F sends 2 to B, let's say, F sends 3 to B, let's say, and F sends 4 to B, let's say. Okay, this is your subcategory. I mean, it is supplied with the identity maps. Every object in every category must have identity. So this is identity on this object, the identity map on this object, the identity map on this object. Check that this is a category itself, right? There is nothing to compose actually. You can just compose F with identity, you can just compose F with the other identity, and that's all that you can compose. And you can compose identity with itself, or the second identity with itself. That's all that you can compose. So this satisfies all the properties of a category. It's a category. C is a category with exactly two objects and exactly one arrow. Now the point is this, that this arrow F is vacuously a monomorphism, right? Because if it were not a monomorphism, then what you could do is you could produce two maps from some x to 1 to, you could produce two maps x to A, such that F composed with one map is F composed with another map, but the two maps might not be equal, right? But you can never produce two maps from x to A. You can never produce two maps x to A, right? Because the only maps in the category are the identities and F itself. So the point is F is vacuously a monomorphism and F is vacuously an epimorphism. Similarly, you cannot produce two distinct maps from B to some object Y, let's say, in the category, such that F composed with both of them are equal, but the two maps are not equal. Right? You can't produce them. So vacuously, I hope you know what vacuously means, right? So vacuous statements are statements which are made about the elements of the empty set, right? So it's like something like all the elements of the empty set are blue in color. It's a vacuously true statement, because if it were not true, then you could produce one element in the empty set which is not blue in color, which is an obvious contradiction because the empty set doesn't have any elements. So vacuously, F is a monomorphism. In C, and an epimorphism as well in C, right? But F is neither injective nor surjective by our very definition. F is not injective, F is not surjective. So it's not true that monomorphisms need to be injective in C and epimorphisms need to be surjective in C. One set category. Yeah, I got your idea that you take one set and define a morphism. Wait. Define a morphism other than identity, FA equal to A, FB equal to B. Yeah. Similarly, you can, yeah, that also works. That is why I said you need to be careful with the choice of your morphism, because keep in mind this works, but it might not happen in general, because for it to be a category it should be closed under compositions, right? I mean, for it to be a subcategory it should be closed under composition. So other than the identity, if you take a map F, you need to be careful that F composed with itself, F composed with itself, then composed with itself, all of these maps should be in the subcategory as well. But this works, I mean this example works because it basically flips two elements. That's what it does. It's a symmetry, which when composed with itself is your identity. Yeah, so this will also work. But by the way, how is this a counter example? This doesn't actually this isn't a counter example, right? because this is a bijective map. FB equal to A. Oh, FA is equal to A and FB equal to A. Is it closed under composition? A to A to A, and sorry, FA is A and FB is A. Okay, okay. It's a constant map. Okay. So A goes to A, goes to A, B goes to A. Yeah, it's closed under composition. Yeah, it works. This also works. Okay. And you can produce even more complicated examples as well. So idea is that monomorphisms and epimorphisms are not hereditary properties actually. I mean, they are hereditary properties, but the converse is not true. That if something is a monomorphism in the subcategory, it need not be a monomorphism in the original category, in the bigger category. What happens if C is a full subcategory? What do you think? That's a good question. What do you think? Should it be true? Full. So what is a full subcategory? It's a subcategory. So which has, okay. So how should I say this? So C is a full subcategory of D if the inclusion functor from C to D is full as well. It's always faithful. If it is full as well, then I say we'll say that C is a full subcategory of D. In other words, if A and B are arbitrary objects in the subcategory C, then the Hom set CAB is exactly equal to the Hom set in the larger category from A to B, DAB. Yeah, so if C is a full subcategory, is it true that monomorphisms in C are injective set maps and epimorphisms in C are surjective set maps? Yes, exactly. Of course. Because, why exactly is this the case? Because if you take two arrows A to B in your full subcategory C, let's say this is F, let's say this is G, right? Sorry, why do I keep saying two arrows? You take one arrow F and see. My claim is that monomorphisms in the subcategory need not be monomorphisms in the larger category. Because if this is a monomorphism in the subcategory, this means that for every object in the subcategory with arrows arbitrary P, Q, F compose P is F compose Q implies P is equal to Q. To check that F is also a monomorphism in the larger category, what you need to do is you need to consider all objects Y together with in the larger category together with arrows like this, such that whenever the composites are equal, the two arrows should be equal. But that is nowhere guaranteed here, right? That is nowhere guaranteed. That equality is nowhere guaranteed, or that property to hold is not guaranteed, because you don't have control over the object Y. It is an arbitrary object. So it still falls. And you can produce examples. Okay, so let's come to the next question. So let 0 be a zero object of your category. We have already defined what it is. It's an object which is both initial as well as terminal. So you have studied initial objects and terminal objects in a category, and in the next week you will be studying something more general which sort of subsumes the universal properties of initial objects and terminal objects, which are called limits, or rather co-limits and limits. You'll study that in the next week. But for now we know what initial and terminal objects are, and an object is a zero object if it has both an initial object as well as a terminal object. So assume that you have a category C with a zero object which we are denoting by 0. Such a category, by the way, is called a pointed category. Yeah, so suppose C is a category with a zero object, then the statements are, for every object A in C, there is a unique map from 0 to A, right? Unique arrow from 0 to A. The statement is that the unique arrow from 0 to A is a monomorphism. And the statement is that the unique arrow from A to 0, because 0 is terminal, is an epimorphism. So there is a unique arrow from A to 0 because 0 is terminal. So the claim is that this unique arrow from A to 0 is an epimorphism. So is this true or false? do you think? Is this true or false? So 0 is a zero object, implies that 0 is an initial object, which implies that for every object A in C, there is a unique arrow from 0 to A. Is this arrow a monomorphism? Think about this carefully. What do you need to show if this is a monomorphism? If you want to show that this is a monomorphism, what do you need to show? That if you take an arbitrary object C, let's say, together with arrows P and Q from C to 0, such that the composites are equal, then the two arrows must be equal. Is this not vacuously satisfied? Think of, yes. So let's see. So option C. So C is actually correct, and in fact this is true for terminal objects and initial objects. So C is correct. So 0 to A, you have this unique map. Take an arbitrary object C and take two maps P and Q from C to 0. For the time being, let's focus on what we want to show. So let's call this unique map H and assume that H compose P is H compose Q. What do we want to show? We want to show that P is equal to Q. Now think about this carefully. 0 is a zero object, so it's a terminal object. It's a terminal object implies that there is exactly one arrow from C to 0. So we have taken two arrows P and Q, that means that P is equal to Q, as 0 is terminal. Right? So H is a monomorphism. You can also check the other property for epimorphisms. The unique map from A to 0 will be an epimorphism, or dually. Using the duality principle, passing to the opposite category, the unique map A to 0 is an epimorphism. Okay, pretty simple. Okay, the final part, the forgetful functor U from top to set is representable. Who here doesn't know what top is or what topological spaces are? Does everyone know what topological spaces are and continuous maps are? If you don't know, you can write in the chat. We won't be defining the what topological spaces are. We'll just skip the problem. Do all of you know what topological spaces are? So you know what the category top is. Objects are topological spaces, arrows are continuous maps. So I am assuming everyone knows. Okay, so we'll just give a hint to this, not solve it. So the claim is that option D is correct. I mean statement D is correct. Let me just check if it's still recording. Yeah, D is correct. So how do you show D is correct? You want to show that U from top to set, this is your forgetful functor, sending every space X to the underlying set X, sending every continuous map F from X to Y onto the just the map set map F from X to Y. right? So we want to show that U is representable. What do we want to show that means? We want to show that U is isomorphic to top, I mean naturally isomorphic to top uh, some space x comma dash. So the idea would be to find such a space x such that arrows in top from x to y, that is continuous maps in top from x to y, are the same as the elements of the set uy, right? So what should that x be? What can such a space x be? So that continuous maps from x to y are the same as maps from elements of ui. This is just a intuitive proof, because the isomorphism exhibited here should be a natural isomorphism. So not only do you need to show that for every y you have a bijective map from top xy to uy, you also need to show that those bijective maps satisfy the naturality condition. I mean, what I'm trying to say is you want to show, you want to prove that u is naturally isomorphic to top x comma dash, which means that you want to produce a natural isomorphism from top x comma dash to u, to the functor u, which means that for every object y in top, so for every space y, you want to produce a bijective map from top xy to uy in such a way that this map alpha y is natural in the variable y, right? That is, a naturality axiom also holds, by which I mean that you need to show that if you take an arbitrary map from y to y prime in top, which is just a continuous map, then you have this square top xy uy alpha y top xy prime. Often people ignore the naturality axiom or the naturality part of showing that something is a natural transformation, but that is perhaps even more important. The naturality is very important. Naturality in the variable y, alpha y prime uy prime. You have an obvious map ui to ui prime induced by f, which is uf, and an obvious map top xy to top xy prime, because top x dash is also a functor. It's a representable functor. You know what it does to maps in the domain, right? This square should also be commutative. I mean, this square should be commutative. That is what the naturality axiom says. You start with any arbitrary arrow in your domain category, you obtain the corresponding square in the codomain category. You want that square to be commutative, right? This is what the naturality axiom says. So you need to check that alpha y is actually is natural in the variable y, or in other words, you need to check that alpha with component alpha y at the object y is a natural transformation. You need to check that alpha is a natural transformation. This is very important. We'll skip that for the time being, but please do fill out the details. But the question is, what can this bijection be? First of all, what can the space x be? So I'll give you a hint. Try to fill out the details. So hint is, the singleton space doesn't work. That is, the terminal object doesn't work. I mean, normally if I would have asked you the same question in the case of sets, that is, show that the identity functor from set to set is representable, you could just take the representing object to be the singleton set, because maps from singleton set to any set are exactly the same as the elements of the set, right? In fact, this also prompts the notion of something called a generalized element of an object in a category. So as I have been saying, objects in a category do not have any internal structure, right? But you can somehow, or sometimes, you can define a notion of something called a generalized element. Elements don't exist, But based on the idea in the specific category of sets, maps from singleton to a set S are the same as elements of S. You could define a map with codomain S in an codomain B, let's say, in an arbitrary category to be a generalized element of B of shape A, right? So a generalized element of an object B in a category, in an abstract category, is just a map. There is no notion of element of B. It doesn't make any sense, but it's just a name that that we can use sometimes, called a generalized element, because it generalizes the idea of an element. Elements don't exist in an object, right, in an abstract category, but you can talk about something called generalized elements. Yeah, so if I would have asked you the same question in the category of sets, you would have said just take the singleton set, it represents the identity functor. In the category top, the identity won't work, the singleton space does not work, because what are continuous maps from a singleton space to a space Y? Sorry, am I confusing something? Oh, singleton does work. I'm sorry. I'm sorry. The singleton does work. Strangely, yeah. The singleton space does work. Yeah, I only gave you the answer. Because every map from singleton space to a space Y is the same as an element of Y. Yeah. It's continuous automatically. So if you take the singleton space star, let's say, with exactly one element, one point, and the topology is the trivial topology, which is also the discrete topology in for the singleton space, then a map from star to S, let's say A, is an element of S, of the space S, right? And every map from singleton to S is automatically continuous. Yeah, the singleton space works. So yeah, try to fill in the details. I'm sorry, the singleton space I had something else in mind, but yeah, that is not applicable here. Okay, yeah, so we should conclude that statement A is correct. We should put a tick on this. Oops, sorry. Okay, let's come to the next problem. So this is also related to one of the problems in your assignment this week, which talks about the notion of a separator, also sometimes called a generator. So what is it exactly? An object G of a category C is called a separator if the functor represented by G, or rather co-represented by G, is faithful. So you know what a faithful functor is, right? A faithful functor is exactly a locally injective functor, right? The structure maps associated to the functor should be injective. So G is called a generator or a separator if the functor co-represented by G is a faithful functor. So question is, which of the following categories have separators? So we'll do this problem, but okay, let's just quickly reduce this to a simpler condition for separators or generators, and perhaps something which actually justifies the use of the word separator. So CG comma gap from C to set is faithful. What does that mean? It means, by definition of a functor being faithful, it means that for all objects C comma C prime in C, the associated map from C prime to set CG comma C comma CG comma C prime. This is just the map associated at the level of Hom sets, right? For the ordered pair C prime of objects in C. Every functor has such maps. So if F is a functor from a category A into a category B, for every pair A prime of objects of the domain category, you have a map F A prime, right? Which is a map of A prime into B F A prime, right? Similarly, so for A prime you have the map F A prime. Similarly, for some other pair A prime, some other pair, let's say XY, you have a map Fxy from script A x comma y to script B Fx comma Fy, right? So for every ordered pair you have a map, right? The functor is said to be faithful if this map is injective. Now the functor co-represented by G, CG comma gap, is also a functor, so in particular it has a map like this for the ordered pair C prime of objects in C. The claim is that, or it is given that this map is injective. What does that mean? This implies that if you take F not equal to G in the domain, then the maps induced by F and G in the codomain, the images. So let's say the image of the arrow F under your map, which I should write as CG comma gap C comma C prime according to our notation. So functor A comma A prime, that is what we are using. This map suppose sends F to F star and G to G star. How is F star defined? You have seen this. F star is a map, set map from CG comma C into CG comma C prime. What does it do? It sends every arrow H from G to C to the arrow. So G to C to C prime, you have F. So C to C prime comes later. So F composed with H. This is what the map F star does. And what does G star do? G star is again from G C comma C into C G comma C prime, sends every H to G composed with H, right? Now this map is injective, which means that if F is not equal to G, then F star should also be not equal to G star, right? Note that F and G are arbitrary maps. So as CG comma gap is faithful, as this functor is faithful, that is locally injective, that is in other words corresponding to the ordered pair C prime, the associated map is injective. This implies that for any ordered pair, this implies that for any two maps FG in the source C comma C prime, the images F star and G star are unequal when F and G are unequal. What does it mean to say F star is not equal to G star? This means that these two maps F star and G star are unequal, which means that there is some element in their domain at which they don't agree. So F star not equal to G star implies there exists some H in CG comma C, their common domain, such that F composed with H is not equal to G composed with H. That is, F star applied on H is not equal to G star applied on H, which means F composed with H not equal to G composed with H. So what does it mean to say that capital G is a generator? It means that whenever you take two distinct arrows FG from some object C to some object C prime, there should exist an arrow H from G to C such that the composites are unequal, right? This is what it means. This is what we have proved, and you can check that the converse is also true. So check that converse is also true. That is, if the object G has this property, that given any two distinct arrows C to C prime, there exists an arrow G to C such that the composites are unequal, then the functor C G comma gap is faithful, that is G is a separator. So what we have essentially proved is this. So G is a separator if and only if for any two arrows C to C prime F G which are unequal, such, let's write it in words, such that F is not equal to G, there exists an arrow G to C H such that F composed with H is not equal to G composed with H. That is why G is called a separator. It can detect the distinctness between two morphisms. It can see. So I'll use this phrase often while discussing category theory, that an object sees something, by which I essentially mean that by which I mean that there is a map coming out of that object. Okay. So G can see the distinctness. It can detect the distinctness between two different arrows. That is why it's called a separator. It can separate arrows, which many objects can't. So the question right now is, so let's just use this, G can detect the distinctness of arrows. It's not blind to it. So the question asks, which of these categories have separators? So using the equivalent condition that we have just proven, does the category set have separators? Does it have a separator? What do you think? Does set have a separator? Is there an object in set which can separate? So let's write down what it means to be a separator. So 1, for set, if you take X and Y to sets and distinct arrows F and G which are unequal, what does it mean that F is not equal to G? What does it mean to say that F is not equal to G? It means that there exists some little x in X such that F of X is not equal to G of X. So if something is a separator, it should be able to pick out that element X. So what object can pick out elements in particular of a set in the category of sets? It is exactly we have covered this. Just today only we have talked about this, right? What object in the category of sets can detect elements of a set? Just the same thing as in the case of topological, yes, the singleton set, which means that star, which is the terminal object in the category of sets, or the singleton set, right? Singleton star is the terminal object. This singleton set can detect elements. So from star to X, you take these two maps. One is the element, so singleton set works. So from star to X, you take this map which picks out the element little x. You have F, G here which were unequal. So f composed with little x, it's just a notation by the way, let's call it x hat, which sends a unique element start to little x. So f composed with x hat should also be not equal to g composed with x hat. Why? Because f composed with x hat, if it were equal to g composed with x hat, that means that they should agree on all elements of the source set, right? What is the source set? It's singleton. There is exactly one element which is star. So if composed with x hat applied on star, which is just f of x, would then be equal to g composed with x hat applied on star, which is g of x, which contradicts our assumption that fx not equal to gx. So, and since x, y, f, g are arbitrary, so star is the separator, is a separator. The category of sets. What about GRP, the category of groups? Yeah, oops. What about GRP, the category of groups? We have also covered this today. What group can detect elements of a particular group? So check that. What is that group? We covered that today. The integers under addition is a separator for GRP. So GRP also has a separator. 3 is top. Again we have seen this. So fill out the detail. If you have any questions, by the way, you can always post it on the discussion forum, email me, or you can always ask me. A monoid considered as a single object, is it a separator really? I mean, does it have a separator really? If there is exactly one single object, that single object is your what should I say? Should be your separator. If the category at all has a separator, the unique object should be the separator. So the question is it a separator? Is that unique object a separator? Think about this. So I'll keep fill out the details. The answer should be yes. And everything depends on the fact that a monoid has an identity element, or a category with a single object has an identity arrow. What about this? So this is your category. It has exactly 4 objects together with their identity arrows. There are 2 arrows from one object to another object, and there are 2 arrows from the third object to the fourth object, let's say. Does this category have a separator? Yeah, by the way, when I say that there are 2 arrows like this, I mean they are unequal. The 4 objects are also unequal. That is what I mean here. So does this category have a separator? Think about this carefully. A separator is an object which can detect distinctness of arrows, and it applies to all distinct arrows. So this category should not have a separator. So 5 does not have a separator. Fill out the details. Sorry. And 6 says the underlying category of a poset. Does it have a separator? So what is the underlying category of a poset? The objects of the category are the elements of the partially ordered set, and there is an arrow from little x to little y if and only if x is less than equal to y, right? So does it have a separator? In fact, you can say something stronger about this category. So a poset is a thin category, right? Which means that there is at most one arrow from an object X to an object Y in a poset. So all objects are essential or vacuously separators. So 6. All objects are vacuously separators. Because if some object is not a separator, that would mean that you can get two distinct arrows, parallel arrows. You can get two distinct parallel arrows from an object X to an object Y, such that oops, I'm sorry, I might be saying something wrong here. What does it mean to be a separator? It means that given any two distinct arrows, there exists an arrow H such that the compositions are unequal, right? So what does it mean to not be a separator? So an object is not a separator means that if you take two distinct arrows, there should exist an I mean it there is no arrow from G to C such that F composed H is not equal to G composed H, which means that for all arrows H from G to C, F composed H should be equal to G composed H. Yeah. So if some object in a partially ordered set is not a separator, that means if you take two distinct arrows F and G, then all arrows from that object to C when composed with these two distinct arrows give you the same arrow. That is what it means. Okay. Yeah. So this needed some more thought, but still, what do you think the answer should be? So does G have a does your category, I mean, isn't every object a separator? Because if some object fails to be a separator, you could pick two distinct arrows, right? Such that F is not equal. Okay, I'll leave this. I shouldn't say this. I mean, this needs some thought. Try to think about this and fill out the details. I'm not saying that all objects are separators, by the way. Think about this, convince yourself, and then conclude. And please do ask me if you have an issue. I have to. I wanted to get to problem 5 because this is perhaps one of the most important problems in this entire week, and it involves something that you have learned. So let's quickly get to it. We'll probably take 10 minutes in total, so we'll end by 8:05. I hope that is okay with everyone. So you consider this data. You take a category A. You take the category set. You take two functors F and G from A to set, and you take a natural transformation alpha from F to G. And assume that A is a small category. That is, the class of all arrows in A is a set. Now suppose that this natural transformation alpha from F to G has this following property, that whenever you take an arbitrary object A in the category A, and whenever you take arbitrary arrows, that is natural transformations beta and gamma from the functor co-represented by A to F, alpha composed with beta is equal to alpha composed with gamma implies that beta is equal to gamma. Okay. Then you need to show that alpha is a monomorphism in the functor category from A to set. Now, this condition given here looks very similar to the notion of a monomorphism, but there is one slight difference. What is that? What is the difference? To show that alpha as an arrow in the functor category is a monomorphism, you need to show that it's left cancelable. And what does this property tell you? It tells you that alpha can be cancelled from the left, but only for certain natural transformations, namely natural transformations which come out of a co-representable, right? So this is a very restricted notion, right? Left cancellability means, so left cancellability for alpha would mean that if you take an arrow f to g, I mean left cancelability for alpha would mean that if you take an arbitrary functor h and take two arrows beta and gamma from h to f such that alpha compose beta is alpha compose gamma, you should have beta is equal to gamma. Here you are only given that alpha compose beta is alpha compose gamma implies beta is equal to gamma only for arrows beta and gamma whose source object is the functor co-represented by A, is a co-representable functor. Okay, so that is the important thing to be noted here. So let's quickly get to the idea or solution. Yeah, so you need to show that alpha is a monomorphism. So take arbitrary arrows. So we are talking about arrows in the functor category, that is natural transformations. So let's say H, you take one natural transformation beta, you take one natural transformation gamma to F to G alpha, such that alpha composed with beta is equal to alpha composed with gamma as natural transformations from H to G. We need to claim, or we need to show, so our claim is this, that beta must be equal to gamma. This is what we need to show, and that will finish the proof, or that will prove that alpha is a monomorphism, because beta and gamma are arbitrary and H is arbitrary. So we want to show beta is equal to gamma. So assume on the contrary that beta is not equal to gamma. What does that mean? When can we say that two natural transformations are not equal? What does it mean to say that two natural transformations are not equal? So when are two natural transformations equal? Suppose I take A, B, two functors F, G, a natural transformation alpha, a natural transformation beta. When should I say alpha is equal to beta? If and only if their component arrows are equal, right? So if and only if the component arrow of alpha at the object A is equal to the component arrow of beta at the object A. For all A. For all objects A in your domain category. Then we say that alpha is equal to beta. So what does it mean to say that two natural transformations are not equal? It means that there is some object in the domain category such that the component of one natural transformation at that object is not equal to the component of the other natural transformation at that object. So in other words, beta not equal to gamma here means there exists an object. So your domain category here is A, in script A, such that beta at A, which is an arrow, okay, so let's write gamma at A. Beta at A is not equal to gamma at A, both of which are arrows from what to what. So beta is a natural transformation from script a comma bar to f. So okay, so we already used okay, so let's write it in this way. Yeah, I'm sorry. I'm sorry. What is beta? Beta is a natural transformation from H to F. Gamma is a natural transformation from H to F. So beta at A is an arrow from HA to FA, and gamma at A is also an arrow from HA to FA. So as arrows from HA to FA, beta at A and gamma at A are unequal arrows. These two arrows are unequal, right? Now H, F and G are all functors in the functor category from A to set, right? Yeah, so take arbitrary arrows in the functor category because we want to show that alpha is a monomorphism in the functor category. So if H is a functor from A to set, this means that at an object A of A, HA is a set, similarly FA is a set. So HA and FA are sets, and these are arrows in the category of sets, which means that beta A and gamma A are exactly maps in the category of sets. So what does it mean to say that two maps beta A and gamma A are not equal? This means that there exists some element little x in HA, in the set HA, such that beta A of little x is not equal to gamma A of little x. Beta A is a function, gamma A is a map, so beta A of x is not equal to gamma A of x for some element x in HA. Now what do we use to actually use this fact? To actually use this property. What do we use? So we have an element of the set HA, right? What do we use? Tell me. We have an element of the set HA, which is little x. Beta AX is an element of FA. Gamma AX is an element of FA. We want natural transformations. So what tells you how to get from natural transformations to elements? What is that lemma that you studied this week? Yes, by Nobuo Yoneda, the infamous Yoneda Lemma saves the day here. So what does a Yoneda Lemma actually say? So the Yoneda Lemma says that for a locally small category A, in this case we have assumed A is small itself, what you have is natural transformations, the set of natural transformations, from this functor to any arbitrary functor H from A to set. You have a bijection from this set to the set HA, right? And this bijective map is natural in both A and H. We won't be using the naturality in the variable A, but we'll be using the naturality in the variable H. So let's quickly write down what naturality in the variable H means in this context. It means that if you take H and take an arbitrary H prime and take an arrow that is a natural transformation in the functor category from H to H prime, then you should have a square. So nat A comma bar comma H, you have HA, nat A comma bar comma H prime A. You have this bijective map given by the Yoneda lemma. And you have this bijective map given by the Yoneda lemma, and from nat A comma bar comma H to nat A comma bar comma H prime, you have this map. What does it do? It's obvious. Let's call this map delta, natural transformation delta. It sends any you have alpha, beta, gamma, delta, theta. It sends any theta onto delta composed with theta, right? That is what it does. And you have a map HA to H prime. What is that map? That is just the component of delta at A, right? This square commutes. This is what you know. This is what naturality means. So what does the Yoneda lemma say again? It says that there is a bijection from the set of natural transformations from script A, bar, H to the set HA. And this bijection is natural in both variables A and H. We are using naturality in the variable H. Right? So let's try to understand what this actually means in our context. So we have an element little x in HA. So this element little x in HA is given by some natural transformation from this to H, right? So we have some natural transformation from this to H corresponding to the element x. And what does, I mean, how should I say this? Okay. So we have a natural transformation from script A, to H that we have. To use our property, what we need is two natural transformations from this to F, right? We have a natural transformation from this to H. Now tell me, if little x corresponds to this natural transformation, let's call it delta. Oh, sorry, we have already used delta. We can't use it. Alpha, beta, gamma, delta, theta. What other letters are there? Zeta. We have a natural transformation zeta. Yeah. So tell me, if zeta corresponds to an element x in HA, and if you apply the map beta A on that, so to FA you take beta A, so x goes to beta AX. So beta AX is an element of FA, so that should be given by some natural transformation, right? From this to F. What natural transformation does it correspond to? What natural transformation does beta AX correspond to? It should correspond to some natural transformation. What natural transformation should it correspond to? So I'll tell you the thing, the picture again. Zeta from A, bar to H corresponds to the element X in FA. I mean HA. Now you take the element beta A of X, which is an element in FA. So by the Yoneda lemma again, this should correspond to a natural transformation from this to F. My question is, what natural transformation should it correspond to? So beta is a natural transformation from H to F, gamma is a natural transformation from H to F, zeta is a natural transformation from this to H. So what natural transformation from this to F can you possibly have, which corresponds to beta AX? The answer should be, it should be beta composed with zeta, right? So, and in fact we verify this using the Yoneda lemma. That is what the statement of the Yoneda lemma says. That is what the naturality implies. So you take from H to F, you take beta. The naturality says that, so you have a map from HA to, so H prime gets replaced by F, right? And this map, what is this map? This map HA to FA, this map is just beta. I'm sorry, beta at A, right? And what is this map? Theta goes to beta composed with theta, right? Yeah. So what you do is you take zeta, which was already given to you, which corresponds to the element little x in H. Go downwards first. So you arrive at beta composed with zeta and go downwards along the in the right hand side. So you have beta ax. So beta composed with zeta should correspond to beta ax. That is what the commutativity of the square exactly says, right? The square commutes says exactly this, that beta composed zeta should correspond under the Yoneda bijection that you have to the element beta ax. So there you go. So beta composed with zeta, which is a natural transformation from script a comma bar to f, corresponds to beta a of x in fa. Similarly, you also had gamma, right, from h to f. So gamma composed with zeta from script a comma bar to f corresponds to gamma a of x in fa, right? Now what do you know about beta ax and gamma ax? So beta was assumed to be different from gamma, right? So beta not equal to gamma implies beta a not equal to gamma, which implies that is how we got the element x, right? Which implies that there exists an element x in Hs such that beta ax is not equal to gamma ax. So beta ax and gamma ax are unequal, right? Which implies beta composed with zeta should not be equal to gamma composed with zeta, as beta ax not equal to gamma ax. Precisely because you have this bijection, right? That is what the Yoneda lemma says, from the set of natural transformations to the set of elements of fa. If two elements in fa are unequal, then the corresponding natural transformations cannot be equal as well. So beta composed zeta and gamma composed zeta should not be equal. What did we assume at the beginning? We assume that alpha composed with beta is alpha composed with gamma, right? So alpha composed with beta is equal to alpha composed with gamma. So how can you conclude now? I mean, we wanted to show beta is equal to gamma. We instead showed that we instead assume that beta is not equal to gamma. So we should arrive at a contradiction, right? We haven't used this property yet, right? That if we take two maps beta and gamma such that alpha composed beta is alpha composed gamma, then beta must be equal to gamma. Yeah, my question is okay, I might have messed up a bit. I mean, messed up the notation a bit. So alpha is from f to f to g, right? Yeah. Alpha composed beta is alpha composed with gamma. We want to show that beta is equal to gamma. We assume that beta not equal to gamma. We arrived at this, that beta, there is some zeta from script a comma to h such that beta composed with zeta not equal to gamma composed with zeta. And we assumed at the beginning that alpha composed with beta is alpha composed with gamma. So what does that mean? That means that alpha composed with beta composed with gamma is equal to zeta. I'm sorry. Just go back and have a look at the notations. I'm pretty sure they are correct. So zeta was your map from this to h, right? Yeah. This is alpha composed with gamma composed with zeta, right? Yeah. So we have this, and just look at what is beta composed zeta and gamma composed zeta. What is beta composed zeta? Beta composed zeta and gamma composed zeta were both maps from script a comma bar to f, right? So there you go. We are in this shape. So let's call this beta prime. Let's call this gamma prime, just to avoid confusion. So treat beta prime or take beta prime to be equal to beta compose zeta, take gamma prime to be gamma compose zeta. What we have is, upon composing with alpha, they are equal. So what we should have is beta prime should be equal to gamma prime, right? That is, beta composed with zeta should be equal to gamma composed with zeta. So the last statement should imply that beta, sorry, yeah, beta composed with zeta should be equal to gamma composed with zeta. This is what the last statement should imply, right? So we have this and we have this contradiction. So beta must indeed be itself equal to gamma. So alpha should be a monomorphism. Okay, nothing hard, pretty simple. Only used the Yoneda lemma and naturality in one variable. So the main idea, the main result used was the Yoneda lemma, which says that given any locally small category A and any object A in A, and a functor f from A to set, then there is a bijective map from the set of natural transformations from script A, to H onto the set HA. Okay, and this bijection is natural in both variables A and H. This is what the Yoneda lemma says. Okay. And yeah, so we have proved the result. Please go back and have a look. Otherwise, I mean, just straighten out the notations. I have used a lot of Greek letters here. I'm sure they are correct. I mean, everything is correct. Just go and have a look, and go and have a look at the argument. So yeah, so in the category of functors from A to set, it is, I mean, we can characterize monomorphisms in this alternate way. Just look at maps out of representables. Check the lift cancelability property. If that holds, then the arrow will be a monomorphism. Yeah, we'll stop here and try to fill out the details in 3, 4, 5 and 6. Do you have any questions? Okay, then we'll stop. Or you can keep in mind, you can always email me, and in case you have any questions, or write up in the discussion forum. That's all. Thank you. See you.